And this is Aula. In this first video I'm going to be talking about the central limit theorem. The central limit theorem is a question of probability. In probability theory, the central limit theorem, CLT, states that given certain conditions, the arithmetic mean of a sufficiently large number of iterates of independent random variables, each with a well-defined expected value and a well-defined variance, will be approximately normally distributed. That is, suppose that a sample is obtained containing a large number of observations, each observation being randomly generated in a way that does not depend on the values of the other observations, and that the arithmetic average of the observed values is computed. If this procedure is performed many times, the central limit theorem says that the computed values of the average will be distributed according to the normal distribution, commonly known as a bell curve. Now let's see how this actually works in practice, because this may not be very clear. Imagine we have a binomial distribution and a Poisson distribution. They're both discrete distributions. Okay. Well, in this case, if our binomial distribution, which we already know depends on two variables, n and p, n being the number of repetitions and p the probability. Well, when n tends to infinity, this is when n is a very big number, large number around 100 or 1,000, okay, and p tends to 0, that is that p the probability is a very small number, okay, 0.1 or something like that, then we can consider that n times p is lambda. This is our binomial distribution, okay, which has two variables, n and p, okay, is equivalent to a Poisson distribution, which has a variable lambda, and that lambda is calculated through the multiplication of the variables n with the variable p. N times p is lambda. Okay, so let's see an example of all this. For example, if I wanted to see the probability of chi, well, let's say a variable chi being greater or equal than 300. Okay, let's imagine that chi belongs to a binomial, and that binomial is a binomial 1000.1. Okay, well, at first we'd have to calculate that binomial for n equals 1000 and O equals 1. Well, we could calculate that same probability of chi being greater or equal than 300, but instead of on a binomial, on a Poisson, which was a p100. Why? Because we could calculate the lambda of the Poisson as n times p. 1000 times 0.1 equals 100. So 1000 times 0.1 equals 100. We get n times p equals lambda. That would explain at first how we calculate the Poisson variable through the binomial variable. But this is the very beginning of the central limit theorem. The real practical part, the real useful part, is when we use a normal variable to calculate a binomial or a Poisson. Okay, so in this case we have a binomial variable which depends on n and p. Okay, and so n tends to infinity as before, and in this case, instead of only counting on n tending to infinity, we also say that n times p is greater than 5, and that n times q, or we could say 1 minus p, is also greater than 5. Okay, remember that q is 1 minus p, okay, in a binomial. So in this case, this would be another very, very simple way of using the central limit theorem, because if n is a very big number and n times p is larger than 5 and n times q is larger than 5, then in that case what we'd have is the equivalent to a normal np comma root of npq. Okay, what does that mean? That means that mu, okay, the mean of that normal, is n times p of the binomial, and on the other hand that sigma, the standard deviation of the normal, is the square root of n times p times q. Okay, well, then we have the equivalent of a binomial in a normal distribution. It's quite simple to use actually, and we just might want to take a look on how it works through an example. So how would we operate these kind of examples? Let's say we have a random variable chi, and it belongs to a binomial as we had before, 1000.1. Okay, then that chi would belong to a normal. Okay, just in the same way, in this case, we'd have to do n times p, which is 1000 times 0.1, which would be 100, and then n times p times q inside a square root. So n is 1000, p is 0.1, and q would be 0.90, of course, because it has to actually add up to 1. Okay, so that would be the square root of 90, or what we could call just the square root of 10 times 3, 3 square root of 10. Okay, well, that's very simple. As you see, we have a normal that depends on n, p, and q. Sorry, a binomial that depends on n, p, and q, and a normal that depends on mu and sigma. And we can see the equivalence here as in mu being n times p, and sigma being the square root of n times p times q. Okay, well, let's see the very last application of the central limit theorem, which is also very useful. It's just like the one we just saw. The only difference is that instead of being a binomial that tends to a normal, we'd have a Poisson variable that tends to a normal. Okay, we have this p of Poisson, and we have the normal n. Both, each of them depend on a series of variables. The Poisson depends on the lambda variable, and the normal depends on two variables, which are mu and sigma, the mean and the standard deviation of the population. Well, in this case, when the variable we're studying in the Poisson, lambda, tends to infinity, this is the limit when n tends to infinity of lambda sub n equals infinity. This is the same thing saying we just have a very, very big lambda. Okay, you have to understand that this doesn't have much more significance than that. Then mu would be lambda in the normal, and sigma would be the square root of lambda. Okay, this is the last equivalence, and we can just use it in calculations and tally-ho and all together. So it's not very complicated. Poisson depends on a lambda, and the normal depends on mu and sigma. So we have how the equivalence works, and we don't need much more than that. In this case, if we had a random variable chi that belongs to a Poisson 1000, this is a very big lambda. I know it says it when it tends to infinity, but well, you can understand that 1000 tends to be a very, very big number. Then that same chi would be a normal 1000 square root of 1000, which is actually the 10 root of 10. Okay, that's very simple. Just get this out of the way and put the 10 root of 10 there on the top. Okay, well, we've seen how each of the central limit theorem applications actually work. Okay, from lambda turning into mu and sigma, to n and p turning into mu and sigma, and n and p turning into lambda. Okay, binomial turning into Poisson, binomial turning into a normal, and Poisson turning into a normal. Okay, well, once we've seen all this, there really is just one tiny little thing we should consider. Okay, we've got both binomial and Poisson going to a normal, actually turning in one into another, but we must remember that both binomial and Poisson are discrete variables, while whilst the normal is a continuous variable. Okay, well, this thing makes things slightly difficult. Why? Because we can't really establish how each point of a discrete variable turns into a point of a continuous variable, because between, let's say, chi greater or equal than 300, we wouldn't have another point, because we'd go from 300 to 301 in a discrete variable. But in a continuous one, well, the things change slightly, and so when we say in a discrete variable that chi is greater or equal than 300, we'll have to say in the continuous variable that chi is greater or equal than 299.5, and this is explained through the Yates theorem that we'll explain in a moment. So I hope you found this useful, and I'll see you around in the next video.